So I'm going to present the work of the Medipix 2 and Medipix 3 collaborations. As Becky just pointed out, we're always working together with people from all around the world. The Medipix 2 collaboration has 17 members. Medipix 3 we had, I think, 22 members in the end. And this is the outline of my presentation. So I'll talk about, first of all, what is ionizing radiation, so what we detect with our particles, what we do at CERN in terms of detecting particles, and how we detect the particles there. And then the question we asked ourselves a number of years ago was, can we use the same technology for other purposes? And I want to show some examples of that towards the end of the presentation. So what's ionizing radiation? Well, ionizing radiation is something which has enough energy, so a particle having enough energy to liberate electrons or atoms or molecules, thereby ionizing them, so you have basically charge deposited inside some kind of medium. And it's made up either of energetic subatomic particles, so those particles which move very quickly like ions or atoms, moving close to the speed of light, or it can be made up of electromagnetic waves, so the photons which are high up in the electromagnetic spectrum. So here is visible light, somewhere down the middle here. And visible light is not ionizing, but once you go above about 10 electron volts, then the particles in this part of the spectrum become ionizing, and those are the kind of things which we can see with our detectors. Now, ionizing radiation exists everywhere. We're exposed to it all of our lives. Part of it comes from the galactic cosmic background. So these are cosmic rays which enter the atmosphere at very high altitudes. And those are composed mainly of protons, and then the rest are heavy ions. But of course, most of those don't get to us on Earth, but they do produce secondaries as they come through the atmosphere. So as they come through the atmosphere, these particles interact with our atmosphere and produce a whole zoo of different kinds of particles. So everything from X-rays to protons, neutrons, electrons, alphas, muons, pions, antiprotons, and positrons. Now, of course, most of those things are absorbed as they go through the atmosphere. But as you'll see later, when you fly, for example, you find yourself up here where there's a bit more of those particles present. Another source of background radiation is solar energetic particles. So those are particles which are coming out of the sun. And the solar wind kind of blows, if you like, charged particles towards Earth. And the Earth magnetic field deviates those particles towards the poles. Now, every now and then, you see there's a kind of burst coming from the sun, and those are called coronal mass ejections. And those emit enough particles that they can a little bit distort the magnetic field of the Earth, and the charged particles are then attracted towards the poles. And this is how we get the northern lights, which you see where I come from in Scotland and even further north. So we're all exposed to radiation all of our lives, and this is just a table which shows the sources of the radiation to which we're exposed. And you can see that on average we get something like 3 of these funny units, millisieverts per year. That's the kind of average. Now, of that 3 millisieverts per year, basically most of it comes from natural background radiation, and in fact you can see that most of it actually comes from the air we breathe, because we breathe in radon, and that's the biggest source of radioactivity which we get in our bodies. Medical diagnostic imaging, so X-rays at the dentist or at the doctors, only constitutes a very small fraction of the average total dose you get. But of course, if you go for many scans, then that can add up. So we have to minimize the dose we give to patients, of course. So what do we do at CERN? Well, CERN is the world's biggest physics lab. We have about 2,500 staff members, something like 800 fellows, 500 students, and 14,000 users. So those users are people who come to CERN to participate in doing experiments for particle physics. And the annual budget's about a billion Swiss francs per year. And so the dark colours here represent the CERN member states, and the lighter colours represent those states which are collaborating in some way with CERN under different circumstances. And the mission of CERN, well, principally, our aim is to deepen the knowledge of the fundamental structure of matter. So we're basically studying all of what matter is made of, and all of the particles we know of are shown in this table here. And of course, in the middle of them all is the Higgs boson, which we discovered back in 2012. But of course, on our way to doing this study of fundamental matter, we have to do things like develop new technologies and facilities. So we make very high energy accelerators for particles. We make very sophisticated detectors. And of course, those detectors produce masses of data which have to be dealt with in our computing facilities. And this is an image of Tim Berners-Lee, who you all know now, of course, who discovered the World Wide Web at CERN, or who invented it, because physicists needed to basically spread information around the world, and he found a very efficient way of doing that, and that's at the origin of even of the game we were playing earlier with your phones. But of course, there are other aspects to our mission, which is to train scientists and engineers. That's an example of some training sessions, and also to basically make cultures and countries work together on a scientific endeavour. So the organisation was running continuously through the Cold War, and involving countries from Eastern Europe all of that time. And these days we have countries basically from all over the world, including countries which are even otherwise enemies, but where people who are scientists come from those countries and collaborate together on scientific projects. So this is an image of the lab. Well, the lab is, what you can see here is the underground accelerator, which is a circle basically, 27 kilometers in circumference. That's Lake Geneva, and this is the Alps behind. And the accelerator image is shown here. That's a picture of the accelerator, which accelerates protons. And at 4 points around the ring, we have these massive detectors which have been constructed around the collision points. So CMS, LHCb, Atlas, and Alice. And that's where we do the collisions of the protons in order to make data, which is then sent to the data centers for analysis. So you can think of it in a funny way. This is a kind of funny way of looking at it. So if you want to look at something at the level of a micron, you like to use a regular microscope. But in fact, what we're trying to see in the subatomic realm is particles in the range of as a kind of attoscope, in the range of attometers. So what we do then is, of course, we have these accelerators colliding the particles and the detectors, analysing the data, and from that we get images like this one here, where we can determine what's actually happened and what were the forces which caused such events to take place. So how do we actually do the detection of particles? This is where I come in, if you like. So in a standard collider detector, we take a bunch of particles, 10 billion protons in this direction, 10 billion protons in the other direction, and we collide them together every 25 nanoseconds. So 40 million times per second, we'd like to make a picture of what's happening to those colliding particles. And so the detector is composed of some kind of tracking medium in the middle, and then a means of measuring energy and further out, and then beyond that, a means of measuring the muons, which are particles which stop in nothing. So basically, you have 10 billion on 10 billion particles colliding in a 25 nanosecond interval, but of those 10 billion particles, only about 20 or 30 actually interact. And the reason for that is that if you take a particle and scale it up to the size of a marble, then even though the beam has been squeezed as much as we possibly can, the next marble to this one would be in Paris. Okay? So that's why of the 10 billion, only a few of them are really interacting, and this is where we have to take these very fast pictures. And this is a slice through the Atlas detector, so it's a segment of the Atlas detector. Where you see really in the middle here, what we're trying to do is basically trace the trajectories of the particles as they leave the collision point. And then there are these particles called calorimeters, which try to stop the particles, where we measure the energy of those particles. And then beyond that, there are muon detectors, which are detectors of particles called muons, which don't stop in anything, basically. Now, one of the signatures that an event in collision has been an interesting one is that we have some muons generated. So those muon detectors on the outskirts of the detector are basically continuously seeking to look for coincident muons, so muons which arrive at the same time. And from that information, we then determine which of the 40 million bunches per second we're going to save to tape. So from the 40 million bunches per second we actually produce, we probably save to tape about 1,000 only, okay? So a lot of the electronics in these detectors goes into selecting just the interesting events and rejecting the rest of the data. So right in the heart of the detectors, we have these detectors called hybrid silicon detectors. And those are composed of a detector readout chip, which is a CMOS chip. It's just like the chip in your phone, except that it's composed into kind of very big pixels. Those pixels are connected to a sensor element, and what happens is charged particles come through the sensor element, they ionize as they go. There's a diode here which is back biased, so this is a means of collecting the charge quickly, and then in the electronics channel here we detect the charge and we try to take this picture. So at the LHC we're colliding 40 million bunches of particles per second, and the role of those chips is to take every single frame cleanly, and then select only one good frame for sending out off detector. And that's a picture of one of our readout chips. This is the Timepix 3 chip, in fact. So here you see the CMOS chip, which is like the chip in your phone, wire bonded down onto a printed circuit board. Then there's the detector on top. These are the little balls of solder which connect the sensor elements here to the readout elements on the bottom. Now, in our pixel chips, they're about 1.5 centimeters square. And in that pixel chip, we have about 65,000 channels. So in your phone, you have 12 million pixels, of course, on a much smaller surface. But in your phone, the pixels have about 3 or 4 transistors each, okay? Our pixels contain about a few thousand transistors, because what we're trying to do in our pixels is detect the charge coming in and then only save information which is interesting. And I'm going to explain how that works in a second. So in the sensor, you have the charge coming in, it deposits charge, there's the electric field, the charge goes down and is detected down here on the readout electronics. And different kinds of particle react with the sensor in different ways. So an alpha particle, which is a very heavy particle, will deposit lots of charge in a kind of plasma here, and that charge will be kind of it kind of self repulses and then spreads down to the readout electronics here, so they make alpha particles give big blobs on the detector. A charged ion heavily ionizes as it goes and might kick out a delta electron as it goes through. A beta particle is like an electron. Well, the electrons only interact with the other electrons in the lattice, so they tend to act a bit like worms. And then photons, depending on the energy of the photon, they have a different means of interacting with the silicon. So by looking at how we detect the particles down here, just looking at the image, we can determine what kind of particle we're looking at. So we can look at different kinds of charged particles and determine a photon from an electron, from an alpha, or from a charged particle. And this is how the electronics on the pixel sensor itself works. So we have a preamplifier, which basically takes the input charge here, it makes a pulse. So this is a 4,000 electron pulse. We set a threshold on this thing here called the discriminator, and then if this charge is above the threshold, then we're going to do something with it. We're going to count the hits. But the important thing is that the fuzziness on the signal here is called noise. And if we didn't have this threshold well separated from the noise, then the image would be fuzzy, okay? So what we want to do is set the threshold so far above the noise that we never get a hit when there isn't a particle. And that's what makes pixel detectors work at LHC. The fact that we have a clean detection of charges, and when there's no charge, there's no detection taking place. And I'm going to show how that works. So this was an old experiment we did back in the 90s, where we hit a lead ion on a lead target, and we had all these particles being produced and going through a whole bunch of pixel detectors. At that time, the sensors were 5 centimeters square. We had 7 detector planes for 500,000 pixels. We took pictures like that. but that was very low precision measurement. We improved that over the years, and in the Atlas detector, they have taken measurements since the start of LHC in about 2010. And this is a single picture of a single one of those 25 nanosecond interactions. So what you can see here are multiple traces here. These are all the particles which have been produced. And what you can see in the little colour circles is that every time a proton has interacted with another proton, we've been able to identify really what happened. So this is a kind of needle in a haystack image. And before the Higgs boson was discovered, there were 10 to the power 15 of those events produced at LHC. And the Higgs boson was discovered on the basis of a few thousand of those being discovered. So the pixel detectors enable you to make this picture of these tracks here because of the clean pictures they take, and that was why they were developed for LHC. But then we asked ourselves, but can we use such a technology for other purposes? Because of course we see that we can make clean images of radiation. So we asked ourselves, what if each pixel just counted the number of hits to make an image, and could each pixel measure the charge in those hits, and could it make, in that case, colour X-ray images? I'm going to explain what that is in a second. And that led to the Medipix chips. And these are the details of the chips, but I'll skip that for now. And then we also asked ourselves, if we want to look at the particles one by one, instead of making a picture, could we do that? And could we measure the energy in every particle which came in on the individual pixels and send all the information off chip? And could we measure when the particle actually arrived in the pixel and also send that information off chip? And this led to what we call the Timepix chips. And that's the details of what are in the Timepix chips. But basically, all of those chips have about 256 by 256 pixels and a 55 micron pixel pitch. So what I'm going to show you now is one of the detectors working. So this is the Timepix chip. I'm going to plug it into the laptop and switch on the acquisition system here. So what I'm doing is I'm taking half-a-second frames, and I'm going to see if there's any radiation in the environment. And happily, you can see that this room is pretty radiation-free. But I brought a little watch, which is an old watch, which gives out high-energy photons, which are going to make electrons inside my silicon lattice, which is a sensor. And I put it on top. And you can see that every time the photon interacts with the silicon lattice, it kicks out an electron, and you have these little worm-shaped electron images on the screen. So with your eyes, you can see what an electron looks like in the silicon lattice. Now, I'm not able to carry radioactive sources around with me, but if I had an X-ray source, I can show you dots, which is what X-rays give on the image, or if it's an alpha source, you have blobs, which is what an alpha source. So if any of you are ever at CERN, I can show you those working in the lab, but I'm not allowed to transport them, especially not by plane. But basically what you can see is that just by your eyes, you can see different kinds of radiation. Now, if we take an image at sea level, so if I took an image in London for 60 seconds, you would see an image which looks something like this one here. So basically not very much hits in the background. If I take the same picture when I'm traveling on the plane, then you can get a picture like this one here. So you can see that, as I mentioned earlier, the atmosphere is really protecting us from radioactivity. And when people talk about a plane which is going to go from London to Sydney by going into some sub-orbit in 1 hour or so, I think you can basically forget that, because the dose which the crew would get would limit the number of times they could actually do that flight, okay? Because the higher you go, the more dose you get, both for the crew and for the passengers. But let's look at some examples of how we can use this detection technology in things other than particle physics. So let's start with what I call colour X-ray imaging. So this is back to the electromagnetic spectrum again. You see that our eyes here can distinguish red, blue, green, all the colours of the rainbow. But when we go to X-rays, when we're going to get an X-ray taken, what people don't tell you is that when you go for an X-ray examination, the doctor is going to look at you and kind of, well, they're not the doctor, but the radiologist, and kind of figure out how thick you are, and the thicker you are, the higher he has to turn up the energy or the photons coming through you. Because no matter how much, say, light I shone through me, nothing would come out. But of course, as you go higher in energy with the photons, then more and more photons will come through the body. But you want some of the photons to be absorbed and some of the photons to make the image. So the thicker you are, the higher the energy has to be. But basically, all of the X-ray detectors used today take the information from the photons coming through the body, and that photon kind of darkens the film according to its energy, or darkens the image on the electronic detector according to its energy. But we lose the information about what energy each photon had. And this is what we tried to solve with colour X-ray imaging, which is what we're trying to do here. So basically, we're trying to take the different energies of photons coming through the body and reconstruct a colour picture of that energy. And so just to explain that, here are 3 images taken with the Medipix 3 chip. If you look on the left-hand side, for the low energy image, you see that there's a good contrast in this part here where the light is thin. It's plastic and lighter fuel. But up here, the image is opaque because all of the photons get stopped, like they would in a heavy person. Whereas if you look in the higher energy image, you can see that you get poor contrast here, but you get much better contrast on the right-hand side here. Okay, so the higher energy photons come through, but they interact very poorly with the little absorbing stuff. So what we can do in colour X-ray imaging is mix the 3 images and make a good contrast image for all parts of the lighter in this case. And this would correspond, in terms of people, to making a better lower dose image of the human body. So our colleagues in New Zealand have been working on that. They made a small animal scanner. They put different absorbing materials into this mouse, and were able to distinguish different absorbing materials in the mouse. But more recently, they made the world's first X-ray image of a human wrist, and this was done using the Medipix 3 chip. Now these colours, of course, are false colours, but it's a different absorption of the bone, of the flesh, and of the fat, which permits them to make this image in colour. So the watch is even there, so they can distinguish well the watch from the rest of the wrist. And this image actually was viewed 40 million times or so on Twitter last year. They also made an image, or an image of the ankle of the physicist there. And if I scan through I'll just stop this somewhere here. Oops. A bit longer. So here what you can see is a very high resolution image of the bone. So the porosity of the bone is a good indicator that the bone is healthy. But then the yellow stuff here is fat, and the red stuff is flesh. So these are things which are impossible to distinguish without having access to the energy information or the colour information on of the incoming X-rays. And there are about 300 million CT scans performed per year. And so our hope is that one day, thanks to these people here, we'll all start to be able to have access to these kind of images. So every couple of years at CERN, we've organised this workshop in medical applications of spectroscopic X-ray detectors. All of the big equipment manufacturers send their people here, and also the major research, medical research schools send people to the meeting. So this started in 2011. At that point, when we began, there was a lot of skepticism about whether such a thing is even possible. But of course, over the years, little by little, I think this year, the conclusion was that we really believe now it's going to get into the medical imaging field soon. But now to switch to another topic, just for fun. So this is a company in Prague which have made a large-scale detector using our chips. These are the Timepix chips. And they made an image. So they have a system with a couple of robots. So one robot holding a microfocus X-ray source, and the other robot holding our detector. And they can scan any shape of object, or even a big thing like a painting. And this was a painting signed by Vincent van Gogh, but no one really believed it was Vincent van Gogh. So that it was kind of uncertain origin. So these guys were asked to make an X-ray of it. And remember, with our detectors, you can see also the absorption in energies, so the colour information. So this is the X-ray picture. You begin to see something starting to take shape here. So I'll kind of an outline here. You can put a red line on there to see that a bit more clearly. So here what you see is the mixture of the front image, which is the countryside of Provence, and the back image, which is something else. Now, by looking at the front image and then using the spectroscopic absorption of the front image, you can subtract that from the back image and then see what's behind. And so what's behind is a female nude. Now, that looks very similar to the kind of nudes that Van Gogh was painting at that time. And we knew that he was very poor during that period of his life. So it could be that if this is ever officially authenticated, it's the first Van Gogh, which will be authenticator being 2 for the price of 1, if you like. So, but that's going to the Van Gogh Museum in Amsterdam for authentication now. And I want to just finally finish off with these. The NASA people are using our detectors in space. So they have 6 of those running constantly on the space station. I showed you an image taken on Earth for 60 seconds. This is an image taken on the space station over the South China Sea. And this is the same picture taken on top of Brazil. So you see there's something different there. And if you make an image of all the radiation seen by those detectors as the space station is flying around the world, you see that on top of South America, they get a lot more dose than they get anywhere else. And that's because there's something called the South Atlantic anomaly, which is due to the fact that the Van Allen belts come closer to the Earth due to the difference in the rotation and magnetic axes of the Earth. So that's basically the South Atlantic anomaly has been the graveyard for many a satellite over the years. But now we can really monitor what's happening to the astronauts there. So in 2014, they flew 2 of our detectors on the Orion rocket launch. They made a movie of the trajectory. So as they went around the Earth the first time, in low Earth orbit, you see this dark blue. So this means that the dose that they were seeing there was relatively low. But over the Cape, the second time around, they blasted off into outer Earth orbit for the first time in many years. And you see the colour starts to change. And in particular, it becomes red as they go through these Van Allen belts, which are these charged particle belts which surround the Earth. So when they want to populate the Moon or Mars, and you have to send people there, you have to basically continuously monitor what radiation they're getting exposed to. And NASA have decided that our detectors will be their baseline detectors for future manned spaceflight missions. So just to conclude, ionizing radiation is all around us. We've seen it. We can detect it with our own detector. CERN itself studies the fundamental nature of matter. So the Higgs boson was discovered here a few years ago. Hybrid pixel detectors were developed for the purposes of making sense of the detector at LHC. In the Medipix 2 and Medipix 3 collaborations, we've taken the technology into other fields, and I've given you a couple of examples here. So color Xray imaging has significant potential for medical diagnostic imaging, and we've seen that Timepix chips have been detecting background radiation in school classrooms and in cultural heritage authentication and in space. And then finally, I'd like to end with a question for you. So what experiment can you imagine to do with this kind of chip? So thank you for your attention.
Could you use ionic radiation as a way of seeing whether someone could get Alzheimer's disease or diseases as they get older?
Oh, interesting to hear that. Could you use this to look for sort of trigger events for Alzheimer's disease or other diseases?
Yeah, the answer to that is honestly I don't know.
Yeah.
What spectroscopic imaging gives the opportunity of doing is to inject a tracer into the body. Now, normally the tracers we inject for doing this kind of work are radioactive, so we look for radioactivity coming from the body. But what we could have the opportunity of doing here is to inject a tracer which contains a particle or a metal nanoparticle which absorbs X-rays at a given energy. And so we could possibly do some, let's say, functional imaging of the body using tracers which are not radioactive for the first time. Now, specifically on Alzheimer's disease, I'm completely unqualified to answer that, I'm sorry.
That's exactly the sort of thing that potentially people will be looking to use this for, you know, as they develop this whole, if this gets into all hospitals, you know, that potential in the future. That's just the sort of question. Brilliant. Any other quick questions, folks? Yes, at the back. Shout.
Going back to your 3D X-ray image, what's like the voxel size on it? How accurate can you image things?
I think it's of the order of 1/4 of a millimetre, something like that. So it's significantly better than anything available. So the pixel sizes themselves are 55 microns. No, in fact, they're 110 microns in this case. So the resolution, let's say the images I showed you of the painting, and then of the human ankle had, its voxel sizes of the order of the 100 microns. It's probably a bit more than 100 microns because of geometric effects, but it's let's say record-breaking. I think nothing else can do that.
Can I just quickly ask, Michael, how long do you think it will be before this becomes the standard way of having an X-ray in hospital?
Well, I mean, at the spectroscopic workshop, there are, as I said, the big companies come there. They, of course, are not using Medipix. They have their own internal developments. But we are kind of pathfinding, if you like, for them, showing what's the kind of optimum pixel size and that kind of thing. Both Siemens and Philips have prototype scanners in use in hospitals. And in fact, there was a nice presentation at our last workshop by a radiologist from Maryland Hospital, which is in the US, where they have lots of gun shotguns. And, but he showed some images of the skull. And he was able to show that, so basically, if you don't use a spectroscopic detector, let's say the edge between the hard part of the skull and the brain becomes very blurry. Okay, it's difficult to see. When you add the spectroscopic information, you can well determine the skull edge from the brain, and then he could see bleeding near to the skull edge, which was something he couldn't have done without having access to spectroscopic information. And that was with what we call a relatively lousy spectroscopic detector. But in the beginning, when we started the spectroscopic X-ray work, well, first of all, we didn't know it would be possible, and then secondly, we didn't know would it be any use? would there be any real extra diagnostic information there? But the conclusion seems to be coming that, in fact, there are things we can see which are otherwise not possible to see. So the big companies are, of course, watching each other very carefully, and since they've been sending significant groups of people every couple of years, you can imagine that internally there is some work going on, and I'm pretty confident it will come.
That's brilliant. Right, I think if there are other... Oh, one quick question there, and then you can ask Michael some more later. Yes?
How accurate is the interpretation of the images? Could you potentially mistake an alpha for a beta particle?
Yeah, so that's up to the... that's kind of up to you or the user. So you have... What the detector will give you is... I didn't show it, but we have a detector called Timepix 3, which has arrival time information as well, which actually gives a 3D image of the way the energy has been deposited in the sensor. So what you get from the detector is a 3D picture of that information, and then it's up to you as a user either to write an algorithm which can distinguish an alpha, beta from gamma, or yeah, I think it's, we can give what the detector can see, and then the interpretation of that is basically up to the user.
Brilliant. Now, I think you'll join me. That was a fantastic talk and such implications for all of us. So thank you so much, Michael. And he'll be around all day and talking to you at your posters. So can we hugely thank him, please?